Last class we talked about density curves. So today we're going to talk about the most famous of all density curves, the normal curve. The normal curve was first described by a mathematician named Gauss. Gauss was so awesome that the Germans actually put him on their money. They don't make the $10 Deutschmark anymore because everybody in Europe is using the euro. But, I'm sorry, that's not the perfect euro. Anyway, so should be more like that. The euro, don't need to write this down, but he actually created this formula, which if you look real carefully is actually on the money, that would accurately describe the normal distribution. We talked about last class that if we had a density curve and we could find the equation of it, then we could start making really accurate predictions about the area under the curve. And if you'll notice some of the variables in here, E is a constant, pi is a constant. So the variables are sigma and mu define it. And so if you remember, mu is the population mean, and sigma is the population standard deviation. And so what we have is we have an equation that will describe any normal population, and we'll discuss what normal means in a second. It doesn't mean kind of the typical population, as long as we know what these two variables are. And so normal should be capitalized because it's a name. It's not, it comes from a period of math where numbers were considered perfect. And so this is a proper noun. It is kind of like, instead of Planck's constant, it is the normal distribution. And it's an important class of density curves, and they describe what are known as normal distributions. All normal curves are symmetric, single-peaked, and bell-shaped. If you ever heard the term the bell curve, they're referring to a normal distribution. That is the bell curve. A specific normal curve is described by giving its mean, which is the center, and its standard deviation, which is there. And since we're talking about entire populations, we will not be using x bar and s sub x. Instead, we will be using mu and sigma because it's the entire population. And what we will see here is that there are several different, the normal curve can be basically, if we give you the mean and the standard deviation, you create slightly different curves. So for the red curve and the green curve and the blue curve, they're all centered at 0 with an average of 0. But they have different, and for whatever reason in this graph, this is not the standard deviation. If it's squared, remember that's the variance. To find the standard deviation, we take the square root. But the green one is going to be the important one, because if you take the square root of 1, you still get 1. And so the green one is one where the mean is 0 and the standard deviation is 1. And so you can move the curve around a little bit, but overall you're always going to get this bell-shaped curve. Remember, it's a density curve, so the area under the curve always adds up to 1. So I told you that was the standard. What you'll see is that this point here, one standard deviation away from the center. So let's say the center was 0. So this is going to be, actually we'll just call this mu. So if this is mu, then this is mu minus sigma, because that's one standard deviation away from the center. So this is going to be mu minus 2 sigma. This will be the mean minus 3 times the standard deviation. And this will be the mean plus the standard deviation. the mean plus 2 times the standard deviation, and the mean plus 3 times the standard deviation. And these points are standard, is how it works on any normal distribution on the normal curve. Now these 2 points I circled here are the points where the graph exists 1 standard deviation away from the mean. And what you will see is that the graph goes from being what's known as concave down to concave up. And this is what's known as the point of inflection. And so when you draw your normal curve, when you're labeling it, the 1 standard deviation away from the mean always has to be this point where it changes from curving down to where it changes to curving up. Once again, a normal curve is going to be described by its mean and standard deviation. And what we'll see here is that you'll actually write this notation where you write what the actual mean of the curve is and what the standard deviation of the curve is. We just talked about that the center is going to be the mean. That's always going to be the center of the symmetric distribution. The standard deviation is that inflection point where it changes curvature from concave down to concave up. And we will denote different standard deviations with this notation. So let's, normal distributions are good approximation of real data. They are also good approximations of chance incomes. And basically, we got to know this because almost all of a very large portion of the statistical inferences that we're going to use are going to use normal distributions. So we need to have normal curves down cold. Normal distributions happen a lot. It's standard, there's a lot of things that if we just took the measure of every newborn child, they would be normally distributed. Height among humans, normally distributed. Weight, ACT, SAT scores, intelligence or IQ, number of typing errors, chemical processes. These are all things that if we plot all the data, they form the normal curve. This IQ one is very important for moving forward. And if we learn nothing else from stats, or you drop out at this point, is we said that, let's go back to the normal curve here. We said that here, so if this was IQ, this center point is average IQ. We said the area under the curve is 1. And the distribution is symmetric, which means that this portion of the graph here is half the graph because it's symmetric. So the area here is 0.5. Or 50%. So why is that very important with IQ? Well, if this is average IQ, then half the population is below average intelligence. It's important to remember that when dealing with the average person in the world, is that half of all people, by definition, are below average IQ. Now, that does mean that half of all people, by definition, are also above average IQ, but those are the people that, are fine. It's these below half average IQ are the people that you don't want to get behind to when they're in the self-checkout lines at the grocery store. So here's an example of normal distribution. Here's a professor. This is a famous, there's a bunch of pictures like this. You'll see them with the military too, where they line up everybody by height. And so everybody here, here's 5 foot, and they basically it's like if you're 5 foot here, if you're 5'1", get here, 5'2", so forth and so on. And they line everybody up, and then they take the picture, and sure enough, if everybody stands where their height is, you get a normal distribution. And we could do this as well. You'll see this everywhere. Now, here is where it becomes important, and this is the empirical rule. And you learn this in Algebra 2, which is that the area under the graphs, and these are not exact, these are approximates, is the 68, 95, 99.7. is that 68% of all data in a normal distribution, or 0.68 of the area, is within one standard deviation of the mean. "95% of the data is within two standard deviations, and between this point and this point in the curve, you can see all we have are these little teeny tails left. That's going to be 0.997. And so early on, we need to memorize 68, 95, 99.7. Now the other thing is these are pieces. The graph is symmetrical. So if this area in red is 0.68, then this half of that area is 0.34, just 68 divided by 2. And we can start to find what are all the little chunks of all of this. Right? If from here to, if the area in blue here is half of 95, 0.45, but we already said that this area here was 0.34. If we subtract that out, then, I'm sorry, this is 0.445. Half of 95 is 0.475. And so the area here shaded in blue is 0.475 minus 0.34, or 0.135. And so we can start to cut the graph up into little pieces and find out what each chunk is. So, but you might say, who cares? But now we know that 13.5% of the population will be between one standard deviation and two standard deviations above the average. And we can start to make predictions about things. We said that height and weight are normally distributed, and all of a sudden, if you're opening a store, you can start to say how many smalls, how many mediums, how many larges, how many extra larges you're going to need to carry in the store for the basic customer. What you can do is we can turn all data into z-scores. We can take our entire data set and turn them all into z-scores, right, using this formula, which was different than we learned last unit, because last unit we were using x and s sub x. But here we have the entire population data, so we're going to use mu and sigma. If we do that, so why? So we take every data point in our thing and we turn it into a z-score. Well, if we do that, then we get the same graph with the same equation, and we can start to map this equation out. And we can start to not just look at the distances between solid standard deviations, but we can start to find the values of every single z-score. And this table is in the back of your book, and what we are going to be doing in class is we're going to be finding specific values in all of these things, and we'll be getting to that in the class. So I will see you guys next class. Read up in the book if I feel like I went a little quick. See you guys next class.